Welcome to our second lesson on exponential functions. We're going to apply what we learned in the last video to some exam questions. Okay. Before we move on, it might be a good idea to look back over growth and decay. So growth is a situation like we see here in the first graph, and when we have a function, if the base is greater than 1, we will have a growth scenario. So for example, if we had 2 to the power of x, that will be a growth. If we have 3 to the power of 0.1x, that will be growth. Okay, so it's okay for the x to have a coefficient. Okay, the next one, 4 to the power of 5x. Again, it's fine to have a coefficient, and that would be a growth scenario as well. Let's have a look over here at the k though. Okay, y equals a to the power of x again, but this time a is less than 1 and greater than 0. Okay, so we're talking about numbers like a half to the power of x, for example, or y equals a quarter to the power of 0.5x, for example. There's something crucial that I really need to point out here that you wouldn't have seen in the last video. We know that a half can be written as 2 to the power of minus 1. So we have 2 to the power of minus 1 times to the power of x, and we know from our index laws that we can write that as 2 to the power of minus x. So this time we actually can write it where a is greater than 1. So it's a little bit of a contradiction, but we're able to do that when we have a negative coefficient in the power. If we look at y equals a quarter to the power of 0.5x, again, we can write a quarter as 4 to the power of minus 1. Okay, so that leaves us with 4 to the power of minus 0.5x. So here, our base is greater than 1, which is fine, but also you can write it as with a negative coefficient. So to summarize, we have got growth if a is greater than 1 and the coefficient is greater than 0. Here we have decay if, two scenarios, a is between 1 and 0 and the coefficient is positive, or if a is greater than 1 but we have a negative coefficient. Okay, so if we have a look at this example, we've got two functions here, one pt and one qt, and I can see that the coefficient here is 0.1. 0.1 is greater than 0, it's a positive number, so this would be a growth model. If we have a look at qt, we actually don't know what the coefficient here of t is. That's probably what you would have to find as part of the question. If k is positive, then it's growth, but if k were to be negative, then it would be a decay model. Before we move on to the real life examples, I want to have a look at initial values and explain their importance. So if you consider the graph over on the right, we've shown in the previous video that we can take negative inputs and plot those values on a graph. And that's quite useful for us in maths. However, when it comes to science experiments you may have done in the past, generally you're dealing with just positive inputs. You're just dealing with, say for example, time. And time you will start at 0 because you can only record from the start. You can't look into the past. So we are concerned with the positive inputs mostly when it comes to real life examples, which means that we're going to pretty much ignore the negative inputs. our starting point is t equals 0 or x equals 0, which means our starting point is the y-axis, which means that our y-intercept is going to be really, really important because our y-intercept gives us our initial value. So the initial value on the red graph there, the initial value there is 1. The initial value on the blue graph is 4. And remember, the reason for that is the coefficient here was 1, so that's why that had a y-intercept of 1. And this one here had a coefficient of 4, so that's why the y-intercept is 4. If you just have a look at the left, this is a linear graph, it's not exponential, and it models the growth of a sunflower over a couple of months. You can tell straight away from looking at that graph that the y-intercept is 2, so that the initial value, when t equals 0, the initial value was 2. We're going to have a look at this Sapphire City example again. Okay, so when you look at Avalon, okay, so I'm just looking at Avalon to start with, you can see that the coefficient here is 3.9. Okay, so our y-intercept is 3.9. In this question, this is just their scientific notation to make it easier, 10 to the power 6. So the initial value here was 3.9 times 10 to the power 6. For the other one, Sapphire City, the initial value is S. And again, in this example, you just multiply by 10 to the power 6 because of scientific notation. The relationship between the number of bacteria in a petri dish, Bt, and the time elapsed T is given by the formula Bt equals Ae to the power of Bt. So B here is the name of the function. It is a function of time, so it changes as time changes. A is the initial value. E is just our irrational number, our base. B is a coefficient. If that's positive, we have growth. If it's negative, we have decay. And T is the value, our variable that's going to change. Okay, so we're given two pieces of important piece of information here. We're told that time equals 0 hours, 100 bacteria are present. So when time is 0, our initial value is 100 bacteria. Then it says 6 hours later, there are 450 bacteria. That means that when time equals 6, 450 bacteria are present. Show that Bt can be represented by Bt equals 100 e to the power 0.25068 t. So we actually have to go through the motions of finding A, finding B, but they've given us the answer there, so we can kind of check that we're right when we're finished. So we're going to use these clues now to help us out. So when time equals 0, B0 is 100. So that means that when I sub in 0, I get 100. Okay, so I'm subbing it in for T. So AE to the power of B times 0 is 0 times, which is 100. E to the power of 0 is 1, so that power is only applied to E, nothing else. And anything to the power of 0 is 1. So that means that A is 100. So once I've found the value for A doesn't change. It's just a constant that I didn't know. So I can go back now and change the function to 100 e to the power of bt. So B0 B6, so 6 hours later, time is 6, B6 is 450. So that means if I sub in 6 into my formula, okay, the answer should be 450. Okay, so I'm just now going to go through the motions of solving this, and I'm going to need logs. Okay, so we've got 100a to the power of 6b is 450. I'm going to divide both sides by 100. Okay, and that's going to leave me with e to the power of 6b equals 4.5. I want to get to the powers. So in order to do that, I'm going to do log b 6b equals log to the base e of 4.5, or 6b equals the natural log 4.5. So that gives me 6b equals the 1.504 and so on. Dividing both sides by 6, I get 0.250679 and so on, which rounds to 0.25068. Okay, so I found A and I found B, and I can sub those back in to get that. Okay, so for any further questions, I can use my formula to help me. So we worked out that it's 100 e to the power of 0.25068 t. How many bacteria will be present after 10 hours? So after 10 hours, t equals 10. So I'm going to sub 10 into my formula. And I can just throw that straight into my calculator. And that gives me an answer of 1,226.561722. You can round this. Now, usually you would round up because it's 5 or more. But the way I would look at this is there are exactly 1,226 because you can't have part of a bacteria. So it said how many whole bacteria are there, and to be honest, it's 1,226. This is a mock question, so it can be quite misleading in that they don't really tell you how to give your answer. So make sure you write down the answer without rounding and then round your answer, just so that they can see that it was just an error in interpreting the question. In truth, an exam question, a proper exam question, will kind of give you more instruction on how to present your answer. How long will it take 15,000 bacteria to be present? Okay, so this time we're not given time, but we are given the y value. Okay, give your answer correct to the nearest hour. So this time we are being given a chance to round. We're being told what to do. So I'm going to sub in as much information as I can into the formula. So BT equals 100. Sorry, getting carried away. E to the power 0.25068 t, and that is equal to 15,000. So I'm going to solve this equation. I'm going to divide both sides by 100. Okay, so that leaves me with e to the power of 0.25068 t, and over on this side it leaves me with 150. Now I need to get at the power. I need to kind of undo the power as such, and remember that the inverse of an exponent is a log. So I'm going to get, if I use log to the base e of 150, or the natural log of 150, that leaves me with kind of getting at the power. And then I can divide across by t. So I have log to the base e of 150 all over 0.25068. Put that all into your calculator